Okay, so welcome back, and this time we're going to talk about standard free energy and its relationship with the equilibrium constant. So there's a relationship between the change in free energy, enthalpy and entropy, and we've seen that in some other videos, so you can explore that elsewhere if you need to. We'll go through the equation a little bit, right? We've got it right here, so that's that relationship. So this relationship exists whether the values are standard or not. Alright, though the conclusions that can be drawn from the relationships is determined by the value that we're looking at, whether it's a standard free energy or a regular free energy. And there's another video that you can watch if you're looking to get more information about plain old free energy, which would be drawn up more like that. Alright, and the relationship has a temperature dependency, as we can see based on this term in the equation. And so what happens is, with this term, we can determine the spontaneousness of the reaction. So whether or not it's going to happen spontaneously or not. Alright. When it comes to standard free energy, what we can do is we can use it to give us a predictor of the equilibrium constant value. So in other words, is K equal to 1, is K greater than 1, or is K less than 1? But K equaling 1 doesn't mean that it's at equilibrium. It's going to be at equilibrium. The system will be at equilibrium when K equals 1. But if K is 10, or rather, if Q is 10, then you certainly are not equilibrium, right? So that would be, with a Q equaling 10, that would be associated with a delta G that would be positive. Alright? And the reason for that would be when Q is 10, you have more product in the system than you need, and so the system is going to shift back towards reactance, which means it's going to go in the opposite direction to what's indicated, and so therefore delta G would need to be a positive value. But that's enough about delta G. Let's talk about standard free energy, delta G naught. And so having this, what we can do is we can take a look at certain values. And so we can use this equation here to help us get started. So I'll put that off into this space up here. Now what you'll notice is that it's very similar to the equation that we used with regular free energy. The difference is that these are all going to be standard values. So now delta G is going to equal delta H, which is negative 2600 kilojoules minus, now because we're dealing with standard values, it would make sense that the temperature would be standard thermodynamic temperature, 298 Kelvin. And we're going to need to multiply that times standard enthalpy, which is going to end up being negative 0.431 kilojoules. So we'll cordon that off. And so let's take a look and see what the delta G value is going to end up being. And so we've got negative 2600 minus the quantity 298 times a negative, 0.431 kilojoules. And so the result for delta G is still fairly negative, negative 2471.6 kilojoules. And I feel like I'm carrying a fair number of extra sig figs. It looks to be that probably should be somewhere around 2 or 3 sig figs. So closer to something like this. So with that being said, we have a relatively negative delta G value. And so with a relatively negative delta G value, that takes us to this piece. And so the K should be greater than 1. So that's what we determined. Now if the standard free energy change value had been a positive, then that would have taken us to this piece right here, telling us that the K would have been less than 1. And if it just so happens that standard free energy works out to be 0, then we can presume that K is 1. But that's not what we had this time. This time we had a very negative answer, which means we're going to have a very positive K value, a K value that's way greater than 1. So hope this helps you guys working with these types of problems, and good luck putting it to use for yourself.